we breathe. This process played a major role in creating our atmosphere in the first place, more than 4 billion years ago. Was Io growing an atmosphere? There's only one place on Earth where the answer can be found: the dangerous slopes of an active volcano on the island of Hawaii. NASA volcanologist Rosalie Lopez has come to high altitude to look for the source of Io's atmosphere. At 11,000 feet, Mauna Loa is so remote that more people have walked on the moon than in this alien and forbidding landscape. It's also unique. Io's surface is coated in volcanic sulfur, and this is the only active sulfur flow on Earth. The closest Rosalie will ever come to an impossible dream: to work on the surface of Jupiter's moon.
Io is really a hellish place, but to a volcanologist, it's absolute paradise because of all these volcanoes erupting all over the place and these volcanic plumes erupting all over the surface. It's just absolutely fantastic, and if I could be sure that I would survive it, I'd go there in a heartbeat.
Rosalie and her colleagues have established Hawaii as a living Io laboratory, a testing ground for new theories. Volcanologists need to know how hot Io's volcanoes really are. They could be as hot as volcanoes on the molten Earth more than 4 billion years ago. Temperature measurements of Io from spacecraft have been inconclusive, but a thermal camera can be used to make a temperature model of similar lava flows on Hawaii. By working out how quickly lava cools down, Rosalie can calculate the true temperature of Io's lava when it first comes out of the ground.
Well, it's absolutely incredible. I've got the entire lobe as it comes out. 1, 2, 3, 4. 1, 2.
What we're learning is that the lavas on Io are indeed very hot temperatures of about 1500 Celsius, which are temperatures of ultramafic lavas, and these haven't erupted on Earth for a very long time.
Io's active volcanoes are giving scientists a new way to study a process that's long extinct on Earth. But can they be producing enough gas to create an atmosphere? The active Kilauea volcano releases a plume of sulfur dioxide, just like volcanoes on Io. It's poisonous, so Rosalie and her team must stay safely upwind, and that demands smart thinking.
You can't send aircraft flying through a volcanic plume. That is very, very dangerous. So we had this idea of flying a kite. And also a kite is cheap, is relatively expendable. And what we're trying to do is find out the distribution of temperatures and of particles and of gases inside the plume to model the physics of the plume and how the plumes erupt.
If they can work out how the gases are behaving once they leave the crater, they can apply their findings to the plumes they see on Io.
We see volcanic plumes on Io of several different types. We have plumes like the Prometheus plume, which have more particles in them, and Prometheus is always active. We call it the Old Faithful of Io. And some plumes that are almost pure gas. It's very difficult to image.
Okay, we're logging data. Oh, that's a perfect sample.
Through their study of Hawaii's volcanoes, Rosalie and her colleagues believe they have solved the mystery of Io's atmosphere.
One of the things that we found out is that the plumes create their own atmosphere. So the volcano on Io creates a local atmosphere around it, which can even produce what we call pyroclastic flows on Earth, which are flows where essentially part of the plume collapses and can move, hugging the ground.
They have found that a single volcano on Io can produce 10 tons of sulfur dioxide gas every second.
So the sulfur dioxide is coming out of the volcanoes, is producing a local atmosphere, and also, we think, a more extended atmosphere all around the planet.
Io's atmosphere is 1,000 billion times thinner than the Earth's, just enough to make it light up with the most incredible aurora in the solar system, but no protection against the lethal bombardment of high-energy particles. Without the Earth's gravity and our much thicker atmosphere, our own planet would be defenseless against a deadly rain from the sun. And suppose the sun erupted with an explosion of high-energy particles so vast that our atmosphere could not stop it, because no one yet knows what the sun is ultimately capable of. Years after the Apollo 17 crew escaped a solar flare, a new generation of NASA astronauts goes through training in Houston for missions to the International Space Station. Over 1,500 hours of spacewalks will be needed to build the space station, 1,500 hours of human exposure to the sun. Work is scheduled at times when protection from the Earth's magnetic field is greatest. But it's a near certainty that a major solar event will hit the station during its construction. To save themselves, they'll need warning of the coming storm. But right now, dangerous solar events can only be detected just 10 minutes before they reach the Earth. Research elsewhere has shown that solar storms threaten not just astronauts, but every human being on the planet. At high altitudes, where the atmosphere is thin, a transatlantic flight can expose passengers to the equivalent of a medical X-ray. Long-term exposure may create a leukemia risk for airline crews. And 6 times in the last 3 centuries, killer flu epidemics have stalked the Earth, claiming millions of lives in precisely the same years as maximum solar storm activity. Scientists have yet to explain why. So the race is on to forecast space weather, but this is a science in its infancy. NASA's Joe Davila compares it to our limited knowledge of the Earth's weather more than 100 years ago.
We had observations of the weather in various separate parts of the Earth, but we didn't have a comprehensive picture. And that's where we are with the sun. We have observations of the sun for the last 20 years, but we don't have a real good, long, continuous record that we can truly understand the basic physics that's going on.
4, 3, 2, 1.
White Sands Missile Range in New Mexico is one of the most secret research establishments in the world. Joe Davila is going in search of the ultimate alien storm. He's making last-minute preparations to fire a rocket at the sun.
We prepare all this stuff.
This is the sharp end of science, as solar exploration moves into the 21st century.
T-minus 20 minutes in counting. Operation Alpha Delta.
Joe Davila aims to go beyond the veil of the Earth's atmosphere. Like a weather forecaster watching for a hurricane, he's looking for early warning signs that might be the birth of a solar flare or a coronal mass ejection. This is a $1 million mission and the last chance for a decade to make it count. Every 11 years, the sun becomes significantly more active, and this is a solar maximum year. They set the controls for the heart of the sun.
There it is. It's up.
The tension mounts.
Darn thing gets colder.
Davila knows that the onboard TV camera will capture not just cutting-edge science, but the ride of a lifetime.
10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Plus 15. Plus 20.
The square patch of white sand dunes near the missile range is clearly visible below. The rocket is already at an altitude of 80 miles. The surface of the sun emits ultraviolet light. Usually this would be absorbed by the atmosphere. But now the scientists have a clear view of the most violent storms in the solar system.
Okay, we should be acquiring any second now. Still don't see it. Here it comes the sun. All right, it's coming in. Now it's going to the correct position. Okay, there we are. Camera's running. Start enable. Experiment start.
We know that energy comes from the surface of the sun. It comes from these convective motions that we see. The riddle we're really trying to solve is how does that happen? What is the exact mechanism of that? If we can understand that, then we can predict that. If we can predict how that's happening, we've taken a big step to predicting the space weather. The sun has been around for about 4 billion years now, and has been operating in more or less the same way. Since the space age, we've learned that there is such a thing as space weather, that the sun influences the planets. And it's only been since we've had satellites and space probes that we've known that.
No, it buried it in the dirt right up to the door.
Okay, look on this coax. Man, it's hot, isn't it? Ouch.
Just half an hour after liftoff, the rocket is safely back in Joe Davila's hands. The data gathered on this flight will be used to design a new generation of space weather satellites, an early warning system for astronauts and commercial airlines. But there is 100 years of catching up to do.
And this is a very difficult problem. It's a very complicated problem. If you look at the sun, it's a very complicated place. It's going to take many years to actually understand the physics of this. What we can hope to do within the next few years is develop a capability where we have enough observations where we've seen this type of event on the sun before. Therefore, we know its effects will be something like what we saw before. And I think that type of capability is something we can look for in the near term.
That's iron 14, 334, and iron 15, 335, so that's in there. Definitely see some structure in the lobes.
Well, I'm satisfied that we have data here. To understand how good it is, we need to do some processing on it. And that's going to take a couple of weeks. I'm sure we hit the second target. I think running computer models to generate what the sun is going to look like 3 weeks from now is something that we would like to get to, but we're not going to get there for a while.
The sun is so unpredictable that some scientists believe the storm to end all storms is yet to come. Our star is 4.5 billion years old, but we have only been observing the storms on its surface for 2 decades. In search of more information, astronomers have found stars within our galaxy which are similar to the sun, but produce flares nearly 10 million times more powerful. A solar flare a fraction of this size would cause a catastrophe on the Earth. But there is no way of knowing if this has already happened in the distant past, or if it will happen again tomorrow.
We think that we know what the maximum flare intensity is for the sun, but it's possible that flares 100 times brighter have occurred in the past, and it would leave no trace in history.
If Bruce Suratani is right, a solar storm could totally destroy the ozone layer in the atmosphere. And with no protection from the sun's ultraviolet rays, the food chain would collapse. He has come to Toronto, Canada, to envisage the end of the world.
If there were a flare 100 times or 1,000 times brighter than a typical flare that we see at the sun, it would cause a gigantic magnetic storm, something like we've never seen before. What you're first going to see is this bright aurora occurring in the poleward region, upward from Toronto. The magnetic field starting to get peeled away from the Earth. We're seeing brilliant auroras to the north. This aurora is coming down southward, coming toward the equator, coming toward Toronto.
The aurora borealis usually only happens in the far north, but this is a fireworks display that everyone on Earth is going to see.
Eventually, this aurora will be overhead, and you'll see the particles come down the lines of forest, and you'll see the bright colors. It'll be splashing down upon you.
The electronic control systems in orbiting satellites are being destroyed. Disabled satellites slow down and crash to Earth. The storm carries its own electromagnetic field. This induces a gigantic electric current in all power lines. The worst geomagnetic storm in history caused a total blackout in Quebec in 1989. But now the lights are going out all over North America, Western Europe, and the world. And the rising sun isn't finished. The storm has set up a chemical reaction in the atmosphere that will blast a fatal hole in our last line of defense.
The one protection we have on the Earth is the ozone in our atmosphere. It stops the ultraviolet from the sun, stops it at high altitude so it never gets down to the surface of the Earth. We think that now that the sun is coming up, that we're safe and everything is over. But one thing we've forgotten about is energetic particles would destroy the ozone in our atmosphere. And this will allow ultraviolet to come down to the surface of the Earth. with a giant flare happening at the sun, basically would have a mass extinction on the Earth.
The astronauts who one day travel to the planets will surely have to handle weather at its most extreme. Alien weather. The first humans on Mars will face dust storms that can engulf an entire planet. On Earth, these same storms are held in check by the water that Mars lost long ago. Our planet is a launching pad for the long journey into alien weather. But though our deserts may compare to Mars, a dust storm will never cover the world. The greatest storm of Jupiter will rage forever, a lord of the atmosphere with unstoppable power. Even as they destroy, the worst storms on Earth are dying. Cut off from its power source in the oceans, no hurricane will ever lay waste to continents or dominate the planet like the Great Red Spot. The Earth is a laboratory where we can study these storms in safety and be glad to never feel their fury. Only space weather can reach across the solar system, drenching entire worlds in deadly radiation. Worlds that are a vision of hell. But unless the sun explodes with the storm to end all storms, we will never experience hell on Earth. The atmosphere gives us shelter from our unpredictable star. So far, we have been lucky. The Earth is the only planet with water, dry land, and a dense atmosphere, the unique combination that gives us weather we can live in. Even at its worst, our weather will never wipe us from the face of the Earth. The Earth will never become planet storm. But if we journey to the planets, alien weather is lying in wait, and it's an awesome reminder that there is truly no place like home.